Right. We have done it here. This is what I refer to as the physics approach. It's not the official name, it's just, I'm gonna distinguish between the two methods. I call this the physics approach, where I do the phasor diagram, and then I work everything based on the phasor diagram. The other way to do it uses complex numbers. And the phasor diagram is done at the end instead of the beginning. The master set for this, I take it down step by step, that when I wrote that problem, I was assuming the physics approach. If you're doing the other approach, which I'm going to call the engineering approach, then you would do it in a different order. So I need to leave that up there. I'm going to leave the equations up there. Don't get to need this more definitely don't need that. Notation. All of these are cosine, all of these have the same angular frequency. There is a shorter way of writing this, and so first off, I'm going to show the shorter way of writing this. Instead of writing all of that, I'm just going to write this as 169.7056 volts, and then 0.523599. So this is just, it is just shorthand notation because cutting out, having to write that over and over again. So you're just writing the amplitude and the phase shift.
What does that mean?
That, the angle. That's an angle sign.
And that's just a dot?
Yeah.
That's a point, that's a dot there because it's 0.5. When we put a 0 in front. That works for you.
I don't know, they're better.
Now the angle's going to eat the 0.
Yeah, basically.
And so each of these, this is actually, it's a simpler notation. Also, when we're expressing a phasor, we'll recalculate or look at your notes. And keep the same problem. So in general, if I look at this, and I have a phasor here, we actually, over there, when we're trying to figure out the instantaneous value, we actually are looking at the real component. If I look at this as a real axis and an imaginary axis, I can express the same phasor. So if I have some angle here, theta, then that phasor and some amplitude A, that phasor can be represented by A times the cosine of theta plus an imaginary number times the sine of theta. Now, assume you're used to using I for the imaginary number, square root of -1. J, because we're using lowercase I to represent current, we're not using lowercase j for anything. This is, I've seen this enough that we're just letting j equal the square root of -1. Now, the angle at any particular time is composed of two parts of it, just like we had it over there. So this would be A times the cosine of omega t plus phi, plus j times the sine of omega t plus phi. So we're going to expand it and see where that takes us. I have cosine of the sum of two angles here, so that's A cosine of, you tell me, cosine of the sum of angles. as in cosine of alpha plus beta equals what?
Cosine alpha, cosine beta, plus sine alpha, sine beta.
Plus minus.
Drop Phil.
So that becomes the cosine of omega t, that's just the a on the outside, cosine omega t times cosine of phi minus sine of omega t sine of phi plus j times
Cosine of, I was using alpha and beta, but,
okay, if you say alpha and beta, I'll translate.
okay, so it's cosine alpha sine beta, or it's sine alpha cosine beta?
Traditionally written sine alpha cosine beta, but
Plus the opposite.
yeah, so it doesn't matter the order which you do it. I'm gonna go with the more traditional form, but what you said works also. Times the cosine of phi minus, sorry, for sine it's the same, sine phi cosine omega t. That's what that, that's the j bracket and the a bracket, there we go. Let's go ahead and see if we can mix and match this a little bit. So we end up with, and again, all of this represents that phasor right there. So this becomes a times cosine omega t cosine phi minus sine omega t sine phi, and then down here plus j sine omega t cosine phi plus j sine phi cosine omega t. And yes, I'm now aware that I wrote the c in a bracket. It is that form. I'm gonna get the cosine phi's together, so I got cosine phi and a cosine phi term there. So I have cosine omega t plus j sine omega t times cosine of phi. And then the sine phi terms, got that one and that one. Minus plus negative sine omega t plus j cosine omega t times sine of phi. Sure did mess that up. Okay. What's j squared?
A -1.
Yeah. So what I'm gonna do is I'm actually going to factor j out of that second term right there. So we have a cosine omega t plus j sine omega t cosine phi. So factoring j out. So plus j times j sine omega t plus cosine of omega t sine phi. If you distribute, j times j gets you that negative there, and then that just gets you the j. But what I have right here is the same. I can factor that out, and I end up with a times the cosine of omega t plus j sine omega t times cosine of phi plus j sine of phi. So we started out with just expressing the phasor in complex form, and we've now reduced it down to here. And now we bring in Euler's formula. was first exposed to it, I'm pretty sure you would have had it by now.
Yeah, I don't remember it though.
Flashback, what is e to the I pi? Is that equal?
Is that Calc 3?
Say it again?
Is that Calc 3 or what is
I
that?
don't think it's Calc 3, that was Calc 1.
Oh.
I've seen this on a bumper sticker even.
Is it not?
He was in
too
math.
strong?
They put those on bumper stickers.
What's that?
They sell bumper stickers with those.
Yeah, well, actually, it's that. Sorry to spoil it for you. If you think about e to the I pi in an imaginary real axis, pi would put us over, pi puts us over here at -1. This is Euler's identity. Euler's formula is more general than that. Euler's formula is e to the I theta is equal to cosine of theta plus I or j. Oh, I guess I'm flipping j's and i's there. J cosine theta. That's Euler's formula, which tells us that this becomes a e to the j omega t e j phi. So this is an expression of the exact same phasor.
How nice.
Okay. What does that do for us?
Makes it a lot
It's
simpler.
obvious. The rest of it is just, apply everything that you know.
For the first one.
Euler? Is that just like O-I-L-E-R?
E-U-L-E-R,
E-U-L-E-R.
I think
German.
Paul
Oh,
calls
Euler.
him Euler.
Oh, yeah.
Yeah, that, in German, that's pronounced.
Sorry, yeah, our
course it
teacher
does.
he pronounces it differently.
Oh,
He
okay.
also has
Well, he's incorrect.
Chinese accent, so it doesn't help much.
Just a little bit of an accent.
Yeah,
So anyway,
okay.
Euler. I guess if he went through Ellis Island, it probably would be Euler.
He also drops the R.
Okay. Great. So if this expresses a phasor, so let's say I have a voltage phasor, we'll just do generic voltage phasor, some amplitude e to the j omega t, e to the j, let's call it phi 1. And I have a current phasor, I e to the j omega t, e to the j phi 2. Well, I can then get my either a capacitive reactance or inductive reactance or resistance, depending upon which phasors these are, or the impedance, just by dividing. I get V over I, which is the magnitude. And then I have e to the j phi 1 minus phi 2. Let's see this a little bit in action with what some of the answers we already have. So if I take the voltage phasor for the power supply, which is, that's a better marker, which is 169.7056 volts with a phase shift of 0.523599. Divide by the current in the power supply. And the current is 10.9867. amperes with a phase shift of 0.2826. Well, the math is simple enough. You do that division, and then you subtract the angles. When we were doing this with just the phasors, notice that we will end up with, this will be our impedance. We will have an angle associated with the impedance. Now, what difference does that make? We will get to. So that should be, well, we had the impedance before, but then I erased it, so whatever the number was down here.
15.4464 was the previous impedance. 4464. That's not what I calculated.
And an angle of whatever that difference is, so 0.2. 4. Whatever it happens to be. All right, so step one was first be able to show that we can express the phasors in terms of a complex number, which ultimately reduces to this. And so once we get it, show that it's in that form right there, we can do multiplication with angles just by adding and subtracting the angles. Step two. We need to be able to somehow convert these and then x of L and x of C. So the resistance, x of L, x of C, into complex numbers. So quick math review. One over J is equal to negative J. Anyone with an issue with this? Because you can take that with the math people. Storm into one of their offices and you say, this
J is a complex number?
Yeah, still go with J is square root of -1.
Okay.
So is this still like an alternate way to do the first step, or are we past that?
No, it's still on setting the foundation for, once you get the foundation down, then the rest of it becomes simpler in some cases.
So
Yeah,
this is
no,
still
that makes sense. You can put the radical on the bottom and then do the thing where you radicalize it or whatever.
Rationalize.
Rationalize it, yeah, and then that'll give you the negative J.
Yep. And there's,
So this is still the second, another way to do it?
yeah, this is, first thing I did was just to establish that I can use these complex numbers. Next step is I need to show what is this or this in terms of complex numbers. Let's just go back to a simple circuit of I have an AC power supply and I have an inductor. My voltage from my power supply is whatever epsilon is times the cosine of omega t plus phi minus L di dt equals 0. We went through this before when we were deriving capacitive inductive reactance. We're doing something very similar here. So L di dt, or actually di dt equals epsilon over L cosine omega t plus phi. So I would be epsilon over L omega sine omega t plus phi. So, just doing an antiderivative there. Using this right here, we have that I, the amplitude of the current across the inductor is equal to VL over XL. That's just epsilon over omega L, which is the way I have right there. I skipped a step there. Oh, that's because I'm doing that the wrong way. X of L is equal to VL over I. Now my voltage, this is what we had done before. What I want to get to actually is X sub L is going to be VL over IL. I need to get this all in terms of our complex space. VL is epsilon, I'm just going to put it in using that notation, times epsilon phi. IL is equal to epsilon over L omega times, not times, with a phase shift of, well, if voltage leads this, then this would be phi minus pi over 2. So whatever the phase of the voltage for across the inductor is, I know that for the current is going to lag by pi over 2. If I do that, I get L omega. If I do that, I get an angle of phi minus pi over 2, which is L omega pi over 2, which is just J L omega, or J